All of these images are of beautiful places. And what's the connection between these areas? Yes, they are all national parks and they are all beautiful, but what gives them their unique beauty is the different types of rocks that are there, but also how they have been weathered and modified. And that's really what is common to these areas, and that's what creates the stunning colors you see, the shapes of the rocks, and these overall landscapes. All of these areas start with a basis, which is their rock or their bedrock, and then they get modified by various processes, by wind and water, and collectively these processes are called weathering and erosional processes. In a larger planetary sense, we know that energy and matter is moving around our Earth. We see that in the formation of clouds and precipitation and larger storm systems. But even on a smaller scale, we can see that energy and matter is moving around the Earth. And even within a lifetime, which is a short time geologically, or a year or a season, we can see changes in the landscape around us. Everyone's noticed the different stream bed before and after a major flood, or maybe an hillside before and after a landslide. What we're witnessing is how landscapes evolve over time, mostly due to weathering and erosion. Now, we've already covered a number of processes that create elevation around the Earth. Tectonics, which create massive mountain chains and basins. We've covered volcanism, which create large-scale volcanic edifices. So those are the forces that really create elevation and mountain chains on the Earth. So tectonics and volcanism build landscapes and build elevation and mountain chains, but it's the weathering and erosion processes that reduce elevations and weather away those massive structures and going to even out the elevation of the Earth. So without these weathering and erosional processes, our planet would look really different. So the topics we're going to cover is: why is weathering important? Why do we care about it? What does it do to make our planet diverse? Then we'll talk about what's the difference between weathering versus erosion, because they're really distinct processes and they're often used as a phrase together, but they're very distinct. And then this first video, we'll talk about the physical or mechanical weathering processes such as frost wedging, unloading, thermal expansion, biological activity, and crystal growth. And then a subsequent video, we'll talk about chemical weathering, and we'll talk about processes such as dissolution, oxidation, and hydrolysis. And then we want to finish with talking about how weathering rates vary and what determines how fast these processes occur. So let's dive in. We often talk about weathering and erosion as one, but they are a very distinct set of activities. Weathering is the breaking down of rocks, and erosion is the removal of the byproducts of weathering from high elevations to low elevations. And on a side note, mass wasting is a term that refers to the transfer of movement of rock or soil downslope primarily by gravity. And usually this is considered a somewhat separate topic, although it is really kind of a type of erosion, but it's much more episodic and not the continual movement of material from higher elevation to lower elevations through wind, ice, or water. It's mostly accomplished by gravity, plus some other mitigating factors such as rainfall. So it does accomplish the same thing, but it's not really going to be considered as part of the erosional process that we're going to talk a little bit about today. For the purpose of this class and teaching in general, we often break up these weathering processes into two main groups, the physical and the chemical weathering processes. But that's a bit artificial because they both happen at the same time on the same rocks. So it's kind of a concurrent and a very interactive process. In fact, the rates of mechanical weathering affect the rates of chemical weathering. There are two major ways that rocks break down, either physically or chemically. By physical weathering, which is the same thing as mechanical weathering, the rock breaks down into smaller pieces of the original rock, but the chemistry or the mineral content of the rock has not changed. Chemical weathering, on the other hand, is when the rock interacts with gases in our atmosphere and with water, and it either dissolves the rocks or forms new minerals. So there is a change from the original rock to the byproducts of weathering in the chemical weathering process. Chemical weathering of rocks and minerals is part of an equilibrium process. As you recall, igneous rocks form deep within the earth under conditions of high pressure and high temperature. But then when those rocks become part of the Earth's surface, they are no longer stable to the Earth's conditions, which are lower temperature and lower pressure. So these minerals are very easy to convert to more stable ones, which is what the chemical weathering process is. So the focus of this video is really to dive into the 5 main mechanisms by which rocks physically or mechanically weather: frost wedging, unloading or exfoliation, thermal expansion, biological activity, and crystal growth. These last 2, biological activity and crystal growth, can also be seen as a type of chemical weathering, so the distinction between them is not as clear. The first type of physical weathering I want to talk about is frost wedging, which is the same as frost shattering. And this happens very close to the Earth's surface when there are existing fractures in rocks, or the rock has a lot of empty space called porosity, and water will fill in those pore spaces and fractures. And then if that rock experiences freezing temperatures, that water will freeze. And water has the unusual property of expanding about 9% when it freezes. So when that water freezes, it will push open that already existing fracture in the rock. And then when the rock undergoes a thaw cycle, that water will further penetrate into the porosity or the fractures in the rock and then freeze again, pushing it open even further. So this can serve to pry apart rocks very effectively. So in order for this to happen, you have to be in an environment where there are continuous freeze-thaw cycles. So you would think that a place in the Arctic would be dominated by this type of weathering, but that's not exactly the case, because in really cold environments, it just stays cold for 4, 5, 6, 7 months of the year, and you basically have one large freeze-thaw cycle. But it's the daily freeze-thaw cycle that can really break apart rocks in this manner. So that would be prevalent in any either high altitude environment where there's a big difference between night and day temperatures, such as at high elevations, or kind of mid-latitude regions that experience these changes in temperature. Many landscapes are the result of this as being the dominant type of weathering, and you'll see that in the Sierras, in the Alps, and any kind of high alpine environments. And the rocks in these areas will be really jagged, angular. And the telltale signs of this as a dominant process are these large talus slopes, which are big hillsides made of these rubbly, angular pieces of rock that have been pried apart from the higher elevations. And one of the iconic features that is associated with this type of weathering are what are called horns. You've seen pictures of the Matterhorn that look like this, and all sides has experienced frost wedging to create this very angular feature. The next type of weathering feature is what's called unloading or exfoliation. As I mentioned earlier, plutonic rocks such as granite form deep within the earth and under huge amounts of pressure. There's a lot of confining pressure holding in that rock. But when the material that's above that rock erodes away, pressure slowly gets released, and as this rock is uncovered, and due to the lessening of pressure, it slowly begins to expand. And rocks break apart as they expand just a bit. And they break apart in layers that are parallel to the Earth's surface, almost like the layers of an onion. And this expansion causes cracks, and this whole process is called exfoliation. And the slabs are usually about 1 meter thick that come off of this bedrock. And this can happen rapidly and would result in rock bursts at mines or quarries, or naturally, and the rock, as it expands, fractures off in these layers. And that is what's responsible for some of the most stunning landscapes of Yosemite. Those domes that are kind of the iconic structure of Yosemite are the result of this exfoliation, and they're called exfoliation domes. In addition to the fractures that run parallel to the Earth's surface creating domes, there are often sets of perpendicular fractures that can also develop. And these originate as planes of weakness in the buried rock. And then the unloading that occurs exposes these joints, which end up being fractures that cut through those slabs of rock. And what you end up with are rocks that look like someone sliced through them in a parallel pattern. And these joints are important because they provide conduit for air and water to enter into the rocks and begin the process of chemical weathering. So when you start with rocks that have fractures like this, they often will end up with rocks looking like this, which are called fins. And these are long, linear rock structures that you can see in Arches National Park in Utah. The next type of physical weathering I want to concentrate on is thermal expansion. And this is the daily expansion and contraction of rocks due to changes in temperature. Minerals normally expand and contract due to temperature fluctuations, and this is called thermal expansion. So rocks are composed of various minerals, but the minerals that make up a rock may contract and expand at different rates depending on what minerals they are. So the same temperature changes can make parts of a rock expand and contract more or less depending on the makeup of the rock. And this expansion and contraction of these individual mineral grains can exert a destructive force on the cohesiveness of a rock. It will stress the rock, creating fractures, and ultimately disaggregate the rock. This is especially true in desert environments where the changes in temperature during the day and night may be as great as 30 or 50 degrees C. But because rocks are poor conductors of heat, these daily temperature changes that are occurring within the rock can be as much as 80 degrees C. But note, this mechanism is probably the least effective of all the weathering processes that we've talked about. And it's only really after intensive heat, maybe after a forest fire or lightning strike, that we see a lot of this in rocks. But much more prevalent than that is biological activity. We've all seen an amazing rock that appears to be pried away by a root of a tree. And that's exactly what's happening. Biological activity can cause rocks to break apart into smaller pieces. This type of physical weathering can be accomplished by organisms such as trees or burrowing of animals. Additionally, as the roots grow, they secrete organic acids that will further dissolve the rock. This is a chemical process, and that's why this one process can be thought of as both mechanical and chemical. So the acids that are produced from the roots will erode the rock, giving more space for the roots to grow into. These processes can wreak havoc on sidewalks, fences, and other human-made structures. The last mechanical weathering process I want to talk about is crystal growth, which is also somewhat a chemical process as well, so it can be considered both types of weathering. Salt crystal growth is also called salt weathering, and it's the process by which a saline solution, either from the ocean or from evaporating water, enters the cracks in a rock and evaporates, leaving behind salt crystals. And then when environmental temperatures rise, the accumulated crystals are heated up and expand and release pressure on the rock, causing it to break up. So this can happen in a desert environment, or it can happen in a marine environments where you have a lot of salt spray permeating into fractures in the rock. This concludes our short discussion of the ways that rocks mechanically get broken down into smaller fragments. And all of that happens in place where the rock formed. But that's not the end of the story, because at some point wind or water, or in some cases ice, pick up those byproducts of mechanical weathering and move it from higher elevations to lower elevations. And this process is called erosion. So erosion by wind, water, and ice will affect the particles just in the way that mechanical weathering affects the particles. When the byproducts of mechanical weathering get picked up by water, they get transported in two separate ways. The lighter part of the material remains suspended in the water and becomes part of what's called the suspended load in the upper part of the water column. But the coarser or larger particles end up getting dragged or bumped or kind of moved along the bottom of the stream bed by the water. And that's called bed load. And as those particles get transported by the water, they create a lot of impacts and hit each other, hit the sides of the riverbed, and that in and of itself will affect the nature of the particles that are being transported. This process will serve to break down the rocks into smaller pieces, but will also end up making angular particles much more rounded as the edges get impacted and broken off. So there's a really distinct change in the material that is near where it formed and then where it gets transported further downstream. In general, the particles become more rounded and smaller. And ultimately, the depositional site for most sediment carried by rivers is the ocean or a beach. Not all sediment makes it that far, but that's where sediment is ultimately headed. So most marine sediments originate from rivers that eventually dump into the ocean. So notice the size and shape of most sand grains. In selected areas, wind action can influence the nature of particles that are being transported, as well as rocks that get hit by the sediment-laden wind. Wind imparts stress and may blow particles, such as sand, that can abrade rocks and basically sandblast them. Picture in front of you is a rock that has been sandblasted. You can see the lower part of that rock has a very smooth, rounded surface. That's due to the sandblasting of wind that hit particles against this rock. And what does the continuous impact do to the actual particles transported by the wind? It makes them round like this. So wind can actually produce some of the more dramatic landscapes in certain desert areas, such as dunes, like in Death Valley. So these are landscapes created by wind and sand particles. These are called aeolian processes. Ice, on the other hand, although not volumetrically important, is an efficient way that rocks physically break down. Glaciers are hundreds and thousands of feet thick, and that glacier is like a bulldozer across the Earth's surface. It grinds, it pushes, it moves sediments. Notice the bands of sediments here in a glacier on Mount Baker. That sediment came from bedrock that was ground down by the action of the glacier. And then it can deposit these sediments into big piles of rubble, like this one. As the glaciers grind the bedrock beneath them, they create pulverized rock material called glacial flour. It is silt-sized, which is finer than the smallest grain of sand. And when these glaciers begin to melt, this fine-grained material will become suspended in the outlet streams that drain the glacier, and it turns them a characteristic milky white. Those are some of the main ways in which the byproduct of physical weathering can get moved around by wind, by water, and ice. And these processes not only transport the material, but they will have an impact on what the material looks like at the end of its journey. As I mentioned earlier, physical and chemical weathering happen together on the same rock at the same time. Although we separate these processes mostly to teach them, these processes interact and are part of a positive feedback cycle. In general, the more physical weathering a rock undergoes, the faster the chemical weathering processes will be. So let's dive into that relationship before we talk about chemical weathering. The name of the game here is surface area. Physical or mechanical weathering increases the surface area that is available for chemical weathering. So if a rock is broken down into smaller pieces as it undergoes physical weathering, the chemical weathering will happen more readily than if it's one large piece. Let's take a 2x2 cube or piece of rock. There's 6 sides, each with an area of 4 square centimeters. So it has a total of 24 square centimeters available for chemical reactions to occur. After breaking the rock into 8 pieces, and each piece has 6 sides that are 1 centimeter square, the total surface area now available is 48 square centimeters. So we've doubled the surface area available for chemical weathering by breaking that rock or that cube into 8 pieces. So that is the way in which mechanical weathering can really increase the rate at which chemical weathering proceeds. So this concludes our discussion of the process that physically break down rocks to create smaller particles and mold landscapes. And it's a slow but powerful set of processes that eventually has the power to create these stunning landscapes that we see all around us. And as my grandma Crispin used to say, little by little we go a long way. And that's one way to look at these weathering processes.